Dear friends, welcome to session on turbo machines, on centrifugal pumps and compressors, which is module 5, prescribed by Vishwesvaraya Technological University, Belagavi. And this is Dr. Rudresh from Mechanical Engineering, Government Engineering College, Krishrajpete. So in this session, we would like to concentrate on a pressure rise in an impeller of a centrifugal pumps, minimum speed for starting a centrifugal pump, and multi-stage centrifugal pumps. So let us discuss about a pressure rise in an impeller of a centrifugal pump. So we know that a centrifugal pump is working on a forced vortex flow. That means whenever a certain mass of a liquid is subjected to an external torque, a rise in pressure rate of that particular liquid is going to take place. So that rise in pressure rate in an impeller, that is most important. The magnitude of the rise in pressure rate is directly proportional to the square of the tangential velocity of the impeller at that particular point, right? So this is the one of the important concept. It is the principle on which the centrifugal pump has been based, right? So taking that into considerations, let us see how the pressure has been raised in an impeller of a centrifugal pump with respect to the geometrical parameters which is required for a particular centrifugal pump. It may be a vane angle, it may be the velocity of the flow, it may be the discharge through the respective expression, somewhat like this, right? So let us consider with respect to a velocity triangle. A centrifugal pump is concerned, we know that the discharge is always radial at inlet. That means alpha 1 is equal to 90 degree, VW1 is equal to 0. In that particular connection, let us draw the velocity triangle. Consider the velocity inlet velocity triangle and the outlet velocity triangle for a centrifugal pump. When you see this particular velocity triangles, so very important concept which you can expect from this is that is the vane angle at inlet and the vane angle at outlet. Very important concept. Therefore, we have the vane angle at inlet beta 1. With respect to that, if you apply the tan beta 1, we have Vf1 by u1. If you apply the tan beta 2 for the velocity triangle 2, we have Vf2 divided by u2 minus Vw2. This concept is very, very important because in most of the situation, the one of the important component Vw2, that is the velocity of the wheel at the outlet, that is one of the important component for the respective centrifugal pump to calculate many parameters, right? So it may be a centrifugal efficiency, it may be a manometric efficiency, it may be a mechanical efficiency, or it may be overall efficiency, whatever it may be, right? So Vw2 component is most important component. Consider the velocity triangle at inlet as well as at the outlet. As we have centrifugal pump is concerned, so we know that the total energy at inlet is equal to total energy at outlet minus the work done by the impeller and water. This condition already we have discussed in the previous slides also, right? So let us think about this with usual notations, how we can write this. What is the total energy at the inlet? It is P1 by rho g plus V1 square by 2g plus Z1 with usual notations. If we consider the section 1 as the inlet and the section 2 as the outlet, that is the delivery side, I can write the total energy at the inlet as P, that is P1 by rho g plus V1 square by 2g plus Z1, that is equal to P2 by rho g plus P2 square by 2g plus Z2 minus the head imparted by the impeller to the water. That means the work done per unit weight of the water is U2 VW2 by G. So this condition, this particular expression is very, very important. In most of the situations, Z1 is always is equal to Z2. So that we should not consider for the analysis, right? Therefore, Z1 is equal to Z2. Therefore, if you write the expression for this, we have P1 by rho g plus V1 square by 2g is equal to P2 by rho g plus P2 square by 2g minus U2 VW2 by G, right? So P2 by rho g minus P1 by rho g, that is the total pressure energy at outlet minus the total pressure energy at the suction side. That will gives you what is the rise in pressure inside the respective impeller. That is given by V1 square by 2g minus P2 square by 2g plus U2 VW2 by G. Therefore, P2 minus P1 by rho g, that is equal to pressure rise in an impeller. So this is very, very important. Therefore, if you write this expression P2 minus P1 by rho g, that is equal to V1 square by 2g minus V2 square by 2g plus U2 VW2 by G. So in this expression, so we have initially we can write what is the value of V1. If you see V1 is equal to Vf1 because the velocity of the flow is radial at inlet, definitely I can say that the absolute velocity is equal to the velocity of the flow, that is the radial velocity component, V1 square by 2g. Therefore, minus V2 square by 2g plus U2 VW2 by G. Let us calculate what is the value of V1, that is in terms of Vf1. I can write V1 is equal to Vf1. Calculate what is the value of V2. Calculate what is the value of VW2. You substitute these values, right? So you calculate, you simplify this particular expression. That will give you what is the value of P2 minus P1 by rho g. So in that connection, from inlet velocity triangle V1 is equal to Vf1. From outlet velocity triangle, tan beta 2 is equal to Vf2 divided by U2 minus Vw2. Therefore, Vf2 is equal to U2 minus Vw2 into tan beta 2. This is the value of Vf2. So from this particular expression, how I can calculate the Vw2? Vw2 is equal to U2 minus Vf2 by tan beta 2. That is equal to U2 minus Vf2 cot beta 2. 1 by tan beta 2 can be written as cot beta 2. Therefore, the value of Vw2 I can express as U2 minus Vf2 cot beta 2. V1 I can express as Vf1. And from the same velocity triangle, I can write V2 square is equal to Vf2 square plus Vw2 square. Let me see this. V2 square is equal to Vf2 square plus Vw2 square from this right angle velocity, right angle triangle. In that connection, Vf2 square plus Vw2 square is equal to Vf2 square plus Vw2 square. I can write it as U2 minus Vf2 cot beta 2 square. You solve this expression. Vf2 square plus U2 square plus Vf2 square cot square beta 2 minus 2U2 Vf2 cot beta 2. A minus B the whole square. A square plus B square minus 2AB. Therefore, so Vf2 square, you just take out Vf2 square as the common factor between the similar terms. 1 plus cot beta square 2 cot square beta 2 plus U2 square minus 2U2 Vf2 cot beta 2. Finally, Vf2 square 1 plus cot square beta 2, I can write it as cosecant square beta 2. Vf2 square cosecant square beta 2 plus U2 square minus 2U2 Vf2 cot beta 2. This is the value of V2. You substitute this value of V1 is equal to Vf1. Substitute the value of Vw2 as U2 minus Vf2 cot beta 2. Substitute the value of V2 square as Vf2 square cosecant square beta 2 plus U2 square minus 2U2 Vf2 cot beta 2 in the expression 3.1. That means in the pressurized expression. So P2 minus P1 by rho g, that's equal to V1 square by 2g minus V2 square by 2g plus U2 Vw2 by g. You substitute these values in this particular expression. Therefore, this is the value that I have substituted here. Vf1 square by 2g minus 1 by 2g of Vf2 square cosecant square beta 2 plus U2 square minus 2U2 Vf2 cot beta 2 plus U2 into the value of Vw2 I am substituting here. U2 minus Vf2 cot beta 2 by g. If you solve this expression, I can get y by 1 by 2g into Vf1 square minus Vf2 square cosecant square beta 2 plus U2 square. Therefore, the rise in the pressure rise in an impeller of a centrifugal pump P2 minus P1 by rho g is equal to 1 by 2g Vf1 square plus U2 square minus Vf2 square cosecant square beta 2. This is the rise in pressure rate in the impeller of a centrifugal pump. Next is, let us take one problem related to this. Find the rise in pressure in the impeller of a centrifugal pump through which the water is flowing at a rate of 0.01 meter cube per second. The internal and external diameters of an impeller are 15 cm and 30 cm respectively. The width of the impeller at inlet and outlet are 1.2 cm and 0.6 cm. The pump is running at speed of 1500 rpm. The water enters the impeller radially at inlet and the impeller vane angle at outlet is 45 degree. Neglect the losses through the impeller. So this is the data which is available for us. So D1 is known, D1 is given, D2 is given, N is given. I can easily calculate what is the tangential velocities. Okay. And at the same time, so through this particular expression, one more concept, the discharge through the respective centrifugal pump is given. Yes or no? And at the same time, so the diametrical parameters are also given. That means D1, B1. So all these things are given. So what I can do is, I can calculate the velocity of the flow at inlet. Vf1 is equal to Q divided by pi D1, B1. That means the area of the flow at inlet. The total discharge is equal to area of the flow into the velocity of the flow. Whether we are considering the suction side or we are considering the delivery side, that is secondary. Therefore, the velocity of the flow at inlet Vf1 equals Q divided by pi D1 into B1. From this, I can calculate the velocity of the flow. So, velocity of the flow at outlet Vf2 is equal to Q divided by pi D2 B2. That is equal to 1.768 meter per second. Even in this particular expression, Vf1 is also 1.768 meter per second. The same velocity of the flow we are going to get for both the expressions. Tangential velocities of the impellers at outlet is U2 equals pi dt into n by 60. You can calculate this. It is 23.56 meter per second. Okay. So pressure rise in the impeller P2 minus P1 by rho g, 1 by 2g, g is a constant, Vf1 square plus U2 square. Vf1 we know, U2 we have calculated, Vf1 is equal to Vf2, already we have calculated, beta 2 is given in the problem. Therefore, the rise in the pressure rise in an impeller of a centrifugal pump is equal to 28.13 meters of water. The next concept is, what is the minimum speed for starting a centrifugal pump? This is very, very important. We know that the pressure rise in an impeller is always there. whenever the pump is working. If the pressure rise in the impeller of a centrifugal pump is more than or equal to manometric head, the centrifugal pump will start delivering the water. Otherwise, the pump will not discharge any volume of water through though the impeller is rotating at a very high speed. Very, very important concept. I said that the rise in pressure head in an impeller is directly proportional to the square of the tangential velocity of an impeller. Now I am talking about the square of the velocity, the tangential velocity of an impeller at outlet or at inlet. This pressure rise is directly proportional to the square of the tangential velocity. Yes or no? Even though the pump will not discharge any volume of water if this particular pressure rise is not equal to some quantity of manometric head. So that is there. What is that quantity? If the pressure rise in the impeller of a centrifugal pump, right? If it is not equal to or more than the manometric head, if that particular amount of the pressure rise has not yet been arrived, even though the centrifugal pump is running at a very high speed, the pump will not deliver any volume of water. Therefore, what is the minimum speed at which the centrifugal pump can deliver a water? This is the important concept in this case. When the impeller is rotating, the water in contact with the impeller also rotates. So this is the case of force vortex. So due to force vortex, what will happen? The rise in pressure rate in the impeller is going to take place. Therefore, this rise in pressure rate in an impeller is equal to U2 square by 2g minus U1 square by 2g. What is the pressure rise in an impeller? P2 by rho g minus P1 by rho g. What is P2 by rho g is proportional to U2 square by 2g. The square of the tangential velocity at the outlet. What is P1 by rho g is proportional to U1 square by 2g. Therefore, if I write P2 by rho g minus P1 by rho g, that is equal to U2 square by 2g minus U1 square by 2g. Therefore, whenever the rise in pressure head of a particular liquid in an impeller, if it is not equal to or more than the centrifugal, more than the manometric head, the pump will not discharge any of the water, right? So the flow of water will commences only if the head due to the pressure rise in an impeller is greater than or equal to manometric head. Therefore, U2 square by 2g minus U1 square by 2g. This is the rise in pressure head in a respective system greater than or equal to hm. For a minimum speed, U2 square by 2g minus U1 square by 2g is equal to hm. That is the manometric head. Therefore, D1 and D2 are the inner and outer diameters of an impeller. With this expression, I can write U1 is equal to pi D1 n by 60. U2 is equal to pi D2 n by 60. And the manometric efficiency. So substituting for the manometric head U1, U2 in the above equation, we have that's pi dt into n by 60 the whole square divided by 2g minus pi d1 into n by 60 whole square divided by 2g. That's equal to pi dt into n by 60 into bw2 into eta manometric, because we can write, so in this expression what I can say is the manometric head, right? Manometric efficiency is equal to g into hm divided by u2 bw2. So when manometric efficiency is equal to g into hm divided by u2 bw2, solve for hm in terms of manometric efficiency. If you do this, this is what we are getting. That means U2 VW2 into eta manometric divided by G. Right? If we express this pi d2 into n by 60, right? So this particular thing will get cancels. Pi d2 into n by 60 the whole square, pi d1 into n by 60 the whole square. If you solve this particular expression, therefore the minimum speed to start the centrifugal pump is always given by capital N is equal to 120 into eta manometric into Vw2 into d2 divided by pi into d2 square minus d1 square. This is the actual expression for the minimum speed to start the centrifugal pump. Now let us take one particular problem on this. The diameters of an impeller of a centrifugal pump at inlet and outlet are 30 cm and 60 cm respectively. Determine the minimum speed to start the centrifugal pump if it works against the head of 30 meters. So let us see this. So discharge is given. That means the D1 is 30 centimeter, D2 is 0.6 meters, manometric head is 30 meters, that is available for us, which is also given. Let n be the minimum speed to start the centrifugal pump. Therefore, for a minimum speed, U2 square by 2g minus U1 square 2g by 2g is equal to hm. Therefore, I can easily calculate what is the value of U1 in terms of capital N, pi d1 n by 60, that is 0.03141 n, and similarly for U2 0.0157 capital N. If we express this in terms of this particular expression, U2 square by 2g minus U1 square by 2g, that is equal to hm, right? If you solve for capital N, that is the lead speed to start the centrifugal pump, n is equal to 891.8 rpm. The second thing is the diameter of of an impeller of a centrifugal pump at inlet and outlet are 30 centimeters and 60 centimeters respectively. The velocity of the flow at outlet is 2 meters per second and the vanes are set back at an angle of 45 degree at the outlet. Determine the minimum starting speed of the pump if the manometric efficiency is 70%. Let n be the minimum speed to start the centrifugal pump. Okay, therefore, for least speed, u2 square by 2g minus u1 square by 2g is equal to hm. Tangential velocities I have calculated. U2 is equal to pi dt to n by 60, 0.0157 capital N. So, from outlet velocity triangle, tan beta 2 is equal to Vf2 divided by U2 minus Bw2. Therefore, what I can do is, from this particular expression, I can express Vw2 in terms of capital N. So, minimum speed to start the pump is N is equal to 120 into meter manometric. Vw2 is given and d2 pi into d2 square minus d1 square. Both the systems are available in this case. So, solve for capital N in this case. That is the minimum speed to start the respective centrifugal pump. The next is a multi-stage centrifugal pumps. It's a very important concept. There are two important the purposes are there for a particular centrifugal pump. A centrifugal pump has to discharge more volume of water. A centrifugal pump has to raise the pressure head to a particular magnitude. Right. So both the concepts it has to carry out. Both the performance has to be carried out by the respective centrifugal pump. Right. It is not possible by a single impeller in order to attain the total large quantity of water in order to attain the high head in a particular system, right? So under that situation, so what we have to do is we need to connect one more impeller into a particular system. Either it may be in a parallel or it may be in a series. By that particular situation, what will happen? The performance of a single impeller will be double because there are two impellers are working at a particular time. That particular stage is called multi-stage, right? If a centrifugal pump consists of two or more impellers, the pump is called a multi-stage pump. The important purposes of this multi-staging are: number one is to produce a high head, and number two is to discharge a large quantity of water. If a high head has to be developed, the impellers have to be connected in series. For discharging the large quantity of water, the impellers have to be connected in a parallel. This is the connection of a series connection. Whereas the impeller 1, which has got an inlet, which has got the delivery. Again, from the delivery of the first impeller, a connecting pipe connects to the inlet of the second impeller. Again, it is a delivery. The rise in pressure head of the impeller will take place. The rise in pressure head of a particular water will take place in the first impeller. The same amount of the water which possesses the increased pressure is supplied to the inlet of the second impeller in this case. Again, in the second impeller, centrifugal action is going to take place. Therefore, initially we have got the rise in pressure in the first impeller. Even in the second impeller, what will happen? Again, there is a further rise in the increase in pressure is going to take place with respect to the liquid which has already exhibited its increased pressure. Therefore, the water which is leaving the second impeller has got the highest pressure, which has got the highest amount of the pressure head. Yes or no? Suppose if we have connected n number of impellers across the system, right? We have to keep it in mind that each and every impeller are discharging same quantity of water. So, and each and every impeller are working against a common head, that is the manometric head. Manometric head is always related with respect to a centrifugal pump. It is not with respect to a centrifugal stage. Keep this in mind. So, therefore, this is the respective arrangement, that is the impeller 1 from suction pipe. This is the connecting pipe. This is the impeller 2. This is the common shaft upon which we have connected the respective pumps in series. For developing a high head, impellers have to be connected in series and they have to be mounted on the same shaft. The water from the suction pipe enters the first impeller at inlet and is discharged at outlet with increased pressure. The water with increased pressure from the outlet of the first impeller is taken to the inlet of the second impeller with the help of the connecting pipe. At the outlet of the second impeller, the pressure of water will be more than the pressure of the water at the outlet of the first impeller. But discharge passing through the each impeller is always the same. Suppose if n is equal to number of identical impellers mounted on the same shaft, Hm is equal to head developed by each impeller, then the total head developed by the system is equal to n into Hm. One thing we should remember in this case, manometric head is always related to a particular impeller, not with respect to a stage. Therefore, for calculating the manometric head, we have to keep it in mind that manometric head is the sole particular property of a particular centrifugal pump. Next, multi-stage centrifugal pump for high discharge. If you want to discharge large quantity of water, the pumps has to be connected in a parallel, right? So we have got, so this is the arrangement of that is the parallel connection, multi-stage centrifugal pump for high discharge. We have got an impeller pump 1, we have got pump 2. The outlet of the pump 1 is connected to the outlet of pump 2. Even the pump 1 is lifting the same amount of water from the common sump. Even the pump 2 is also lifting the same amount of the water from the common sump itself, right? If you see the pump 1 is delivering the water, right, through a discharge Q1. Similarly, the pump 2 is also delivering the same amount of the water, right, with a discharge Q2, right. If you see the discharge which is available at the outlet of the stage, it is Q1 plus Q2. That is the delivery pipe 2. It is Q2, it is Q1, therefore Q1 plus Q2. This is the actual arrangement of a multi-stage centrifugal pump for high discharge. For obtaining high discharge, the pump should be connected in parallel. It is very important concept. Each of the pump lifts the water from a common sump and discharges the water to a common pipe to which the delivery of the each pump has been connected. Each of the pump is working against a common head. If n is equal to number of identical impellers mounted on the respective shaft and Q is equal to discharge from each pump, then the total discharge is equal to N into Q. This is very, very important, right? So once when you are talking about this particular situation, the multi-staging is very, very important for the respective high discharge. Let us see some important problems which are related to this particular multi-stage centrifugal pumps. A 3-stage centrifugal pump has impeller 40 cm in diameter and 2 cm wide at outlet. The vanes are curved back at 45 degree at outlet and reduces the circumferential area by 10%. The manometric efficiency is 90% and the overall efficiency is 80%. Determine the total head generated by the pump when running at 1000 rpm, delivering 50 liters per second. What should be the shaft power required to operate? This is very, very important. That means the number of here the 3-stage centrifugal pump is possible. So the number of impellers which are mounted is equal to n is equal to 3, and the diameter at the outlet is 0.4 meters. The width is 0.03 meter. Manometric efficiency 0.9. Vane angle at outlet is 45 degree, which is given. The discharge is LPS. 50 LPS is given. That means 50 divided by 1000, which gives you in terms of 0.05 meter cube per second. N is 1000 rpm, and the area loss is 10%. The effective circumferential area is not 100%, it is 90% times the pi d1 b1 or pi d2 b2, whatever it may be. So calculate the tangential velocities of the impeller at outlet. It is u2 pi d2 dn by 60, which is available. Velocity of the flow at outlet vf2 is equal to q divided by 0.9. See, 10% loss of area has been incorporated. 0.9 into pi dt into b2. From this, vf2 is equal to 2.21 meter per second. From outlet velocity triangle, calculate the value of the tan beta 2. Express the value in terms of tan beta 2. vf2 by u2 minus bw2. The meaning of this particular thing is to calculate bw2. That's all. So calculate what could be the value of bw2. It is 18.73 meter per second. When you go for this, manometric efficiency is available for me. G into HM divided by u2 bw2, because manometric head I need to calculate in this case. Therefore, from this particular expression, calculate what is the value of manometric head. This is 35.98 meters. So I said that manometric efficiency is always related to a single impeller. It is with respect to a pump. It is not with respect to a stage. Therefore, the head against which the centrifugal pump is working, one centrifugal pump is working, is 35.98 meters. Therefore, total head generated among the respective series is HM is equal to N into HM. That gives you 107.94 meters. So to calculate the overall efficiency is related to a stage, but the manometric efficiency is related to a single impeller. Keep this in mind. Therefore, the overall efficiency eta naught is equal to rho g q into HM divided by 1000 divided by the shaft power. Therefore, the shaft power for this particular situation is 66.17 kilowatts. This is the shaft power which is required to drive the respective centrifugal pump, which possesses the overall efficiency of 80% with a total head generation of 107.94 meters of water. Next is, let us think about the second problem. A 4-stage centrifugal pump has 4 identical impellers key to the same shaft. The shaft is running at 400 rpm and the total manometric head developed by the multi-stage pump is 40 meters. Total manometric head developed by multi-stage pump is 40 meters. It is the total head developed by 4 stages. The discharge through the pump is 0.2 meter cube per second. The vanes of each impeller are having outlet angle as 45 degrees. If the width and diameter of each impeller at outlet is 5 cm and 60 cm respectively, find the manometric efficiency. You collect all the data on one side. Therefore, the tangential velocities of the impeller at outlet is u2 is equal to pi dt into n by 60. You calculate that because it is given problem. Velocity of the flow at outlet vf2 is equal to q divided by that is 0.9 pi d2 into b2. That is the area loss, which is not available in this case. So velocity of the flow in the respective systems, right? That is the velocity of flow, which is not possible in this case. Therefore, you just calculate what is the velocity of the flow outlet. Vf2 is equal to q divided by 0.9 pi d2 b2. Suppose if 90% of the equation, if the 10% loss is given, but in this case 10% loss is not given in the problem, so we just calculate what is the value of the full area of the flow, that is 0.2 divided by pi into 0.6 into 0.05. So zero point 0.9 is not there in this case, 10% is not accommodated in the system. Therefore I have considered only the full area of the flow, pi into 0.6 into 0.05, that is equal to 2.12 meter per second. Therefore the total manometric head is 40 meters of water. It has to be distributed among 4 impellers. Therefore 40 by 4 is equal to 10 meters. From outlet velocity triangle, tan beta 2 is equal to Vf2 divided by U2 minus Bw2. Therefore Vf2 is equal to U2 minus Bw2 into tan beta 2. From this particular expression, I can calculate what is the value of Bw2. Bw2 is equal to 10.43 meter per second. Therefore the manometric efficiency, eta manometric, is equal to, as usual, right? So when you write this particular expression, manometric efficiency is equal to G into HM divided by U2 Bw2. If you substitute for this particular expression, we will get the value of the manometric efficiency, which is 74.82%, which is not related to a stage, which is related to a particular pump, because we are talking of manometric head per stage, that means with respect to a particular pump. Therefore 10 meters of the manometric head we have considered for a particular a centrifugal pump. Therefore for a 10 meters manometric head, a manometric efficiency is always related with respect to 10 meters of waters only. Therefore the manometric efficiency is equal to 74.82%. Thank you, friends. So far we discussed about the different concepts related to a pressure rise in an impeller of a centrifugal pump. What is the minimum speed to start the centrifugal pump? Why a multi-stage staging is required for a centrifugal pump? How we can connect for a multi-stage whenever a large quantity of head is required, whenever a large quantity of water is required, and what are the related problems with respect to a multi-staging systems. So in future sessions, we will be discussing more on the respective concepts of centrifugal pump. Thank you.